Good afternoon. We will start our discussions for the content of week 12 for the NPTEL course Smart Grid Basics to Advanced Technology. This is Adyasha Sahoo, a PhD scholar from IIT Roorkee. So this week, basically, we will be seeing the lab demonstration of various concepts that we discussed in the previous week. So we'll see how the setup is done in the lab and how the real-time simulation study is being carried here in the test bed created in the lab. So for the first demonstration, we have this energy management demonstration for a DC microgrid. So you see, this is the DC microgrid, which is embedded in the Palati platform. So this DC microgrid is consisting of various DC sources as well as DC loads. And this DC microgrid in the Palati, so that is connected. So this we are studying for a grid connected state setup. So energy management in a DC microgrid, which is connected to the grid. So this is the PCC, which is realized using a MCB in the lab environment. And then you have this grid side here, which is the AC side. And this you have the DC microgrid, which is the DC side. So between them, you have the converter here, inverter, DC to AC inverter, connected through a filter to the AC side. And here basically bidirectional power flow is possible that we have seen whenever, depending upon the condition of generation and load in the DC microgrid. So it can either inject or absorb power from the AC side. Then we have this capacitor here, which is used to maintain the DC side voltage at a constant voltage. Then we control this inverter performance using this. The control logic is coded in the DSP for the inverter. So basically, we decide the pulses or the duty cycle for the inverter is decided here in the DSP. So depending upon what performance you want, or depending upon the grid condition, how you want to control this inverter performance, that is decided by this block here, and that will generate the required pulses that will be given to the inverter for the functioning. So basically here you see we basically this grid side voltages, currents, grid side voltages, then currents are sensed using sensors. Also the DC side voltage is also sensed and it is given as input to this control logic. You can see this UABC means the AC side voltages, the AC side current, the DC side voltage. So using the sensors, we sense the voltages and currents respectively and give them as input to the control logic. Then the control logic, depending upon the code that is being coded in the DSP board here, so it will then generate the pulses that will be given to the gate driver circuit of this inverter. So pulses are input to the gate, gate driver circuit of inverter. And depending upon this in the pulses, basically the inverter operation will take place. So what is this control logic that is feeded in the DSP? Basically this box that is discussed in the next slide. So there are two control loops here, basically the voltage control loop and the inner current control loop. So basically in the voltage control loop, what we are doing, we are taking this, we have this reference signal for the DC side voltage, and this is the actual VDC, actual DC microgrid voltage that you are getting from the sensor. Then you are computing the difference between them or the error between them, and this error is then minimized using this PI controller here. So to minimize the error, then you get the accordingly the P reference signal that you require, and by then scaling it with the voltage, we get the required current IP star that is required for the minimization of this error between the voltages at the DC microgrid side. So once you know the reference current signal, so that is then passed on to the inner current control loop. So here you see this IP star is given to the current control loop, and IQ star is 0 since we are considering a DC microgrid here. So there is no Q here. This alpha beta are again the uh, AC side current voltages that have been converted into the alpha beta frame. Then we are doing some scaling to get the alpha beta reference currents. Again, then we are comparing it with the actual values here, and then we are minimizing this through the PR controller, and then we convert this alpha beta frame values to the ABC frame values, and we get the reference voltage signals, this VMABC, that will be given to the basically these pulses that will be given to the inverter. Pulses, so these will generate pulses or duty cycle for the inverter. So the main aim of this control logic here is to maintain aim is to maintain a constant DC side voltage for the DC microgrid. So to maintain that, we are calculating the required current, and then we are depending upon the reference current, we are generating the pulses for the inverter operation. So basically this voltage here, V DC, we have to maintain it at a constant value irrespective of the condition of the grid. Then coming next, we see how this is realized in the lab environment basically. So as I said earlier, so the DC microgrid consisting of DC source, that is your PV, and you have this battery energy storage with you. Then they are connected using DC-DC converters to the DC bus, and you have the DC load also here. Now, this DC microgrid that is realized using the OpenRT platform, and this is giving the required voltage signal. This V out you can see here, and from that, this is the power amplifier basically, and in by sensing the voltage here, it is generating the current signal back to the DC microgrid, completing the loop here. Then next you have this inverter, so that is realized using that semicron IGBT stack that we have been discussing from the past few lectures. So the inverter is realized using this device here. Then you have the filter, you have AC loads in the form of bulbs you can see here. Then the PCC is realized using the MCB in the lab. Then the grid performance is basically mimicked using this grid emulator. and this control logic is coded in the DSP. So the performance, the demonstration basically was done for two case studies. For first case, basically the total generation was greater than the total demand for the DC microgrid. And in the second case, there was less generation than the available demand, and the performance was studied accordingly. The next study was for this DFIG setup, where we are trying to see the symmetric and asymmetric fault analysis for a DFIG wind turbine. So for that, the setup that is yes, for that the setup that is being done here is you can see it here. So basically, this is the simulation platform, that is the RSCAD, and this uh, basically voltage that you are getting, that is basically scaled down and given to the GTAO card, and then this GTAO card then is communicating with the power amplifier. Then the input output of this power amplifier is given to the DFIG, which is your test device here. So again, because here the voltage level that you get from the GTAO card is very low, and that cannot drive this DFIG machine, so hence you require a power amplifier in between them. After that, when you have given the input to the DFIG setup, then you then check the performance of this DFIG, check or monitor the device under test, which is your DFIG here. And how you do that? By monitoring its basically voltage and current using the sensors. And this voltage and current values that have been sensed is given back to the RTTS platform through this GTAI card and the filters. So we'll see that how this functioning of the GTAO card and GTAI card is basically done first. So before that, again, this is the picture from the lab where you have different components that are being connected here. So these are the various, this is the RTDS. This whole thing is the RTDS. So you have various racks here. So this is rack 1, 2, 3, 4, 5, 6 racks you have here. And the cards are basically mounted on these racks, this GTAI card and GTAO card. So if you see the previous figure, the GTAO card is to be mounted on the power amplifier and the AI card is to be mounted on the RTDS. So this is the GTA card on the RTDS and this is the GTAO card on the power amplifier. Then this is the DSO where you can see the output on the screen. Then in the earlier you had a DSP based controller. Here similarly you have a FPGA based controller for the we'll see what this controller is used in the DFIG machine. Then you have this converters, rotor side converter and grid side converter. So if you remember the DFIG machine, to maintain a constant stator power at the output, the rotor can either absorb, inject power, that we'll see in the next slide, and that is done using both these converters, rotor side converter and grid side converter. Then in the lower rack here, you see this is the DC motor, which is used to drive the DFIG. This is the DFIG here. So the shaft of the induction machine is basically rotated or the mechanical input to this DFIG is through the DC motor, and the DC motor is controlled using a chopper control mechanism. According to the wind characteristics. So depending upon the wind speed, high or low, you can control the output of this DC motor, and that can be given to the DFIG in turn. So you see, first we see the demonstration for the GTAI card. So where was this GTAI card here? You can see it was in the output side between the device under test and the RTDS. So this device under test, that is realized using the function generator for the simplicity. So this function generator is mimicking the output received output voltage received from the device under test. So basically this part. So basically this is the device under test. This is the device under test. Yeah, so this is the device under test, and we are then monitoring this device using voltage and current sensors. These voltage and current values that you were getting earlier from the device, that is being replaced with the function generator. That is being replaced by the function generator. So the function generator is giving the voltage signal to the GTAI card. So the GTAI card is a 12 channel GTAI card, means there are 12 input pins here, you can see. And then the output of this GTAI card is then given to the RTDS like it was given here. You see the output of the GTAI card was given to the RTDS through the filters, and similarly that is also being done here. The next thing was the demonstration for the GTAO card. So if you see, where was this GTAO card interface between? It was between the input, that is the simulation platform of RTDS, and the power amplifier. The output was given to the power amplifier, input was from the RSCAD or RTDS. So similarly here, from the real-time RTDS or RSCAD platform, the input is given to the GTAO card. That is also a 12 channel based card, and then the output is given. Output was earlier given to the power amplifier. So instead of that power amplifier, we are observing the output using a CRO, oscilloscope, basically. So this is the power amplifier setup. So instead of giving the output to that, we are sensing the performance of the GTO card through this oscilloscope here. So you see here, there is the complete setup for the DFIG. So as this first part is basically the wind characteristics variation. So as I said earlier, a DC motor, so this DC motor of 2.5 kilowatt capacity is used to drive the shaft of the DFIG. And the speed of this DC motor is controlled using the chopper control. And this chopper control mechanism is used to emulate the wind characteristics performance. So let's say you want high wind speed, then the chopper control will drive the DC motor to rotate in a fast way, and similarly otherwise. So the input is AC. So for giving it to the DC side, we have a rectifier here, AC-DC converter. So once you have mimicked the wind characteristics in this block, that is given to the DFIG machine here. So the DFIG will then generate electricity or power. So this power is the P starter. Now we know that the DFIG or this P starter will vary according to the wind characteristics. Now let's say if we have variable wind speed, then the speed stator will also not be constant. It will also vary continuously. But to provide a continuous constant amount of power to the grid side, we are deploying this control here, the rotor side control and the grid side control, to maintain the stator power at a fixed quantity. So whenever this P starter plus P rotor, that is controlled using these two converters simultaneously, is equal to the P grid, which has to be constant, and this is variable. So this rotor can be positive, P rotor can be positive or it can be negative. So if the stator power is in excess, that means in case of high wind speed condition, the P rotor can absorb the excess power available. And in case of low wind speeds condition, the rotor can inject the uh, balance power that is required to maintain the grid at a constant power. Now this then is given to the RTDS and the power amplifier setup here. So this is the power amplifier, this is the RTDS, and that interface is done using the GTAO and GTAI card that we saw here, right? The GTAI card and the GTAO card. After that, we saw the performance of this setup for two case studies in case of symmetrical and in case of unsymmetrical faults. So we see that in case of symmetrical faults, the negative sequence currents are absent because the currents are balanced here. But in case of unsymmetrical fault, you have a negative sequence current also present. The next demonstration, the third demonstration, was the demonstration of ancillary support from the VSG or the virtual synchronous generator. So we have seen in the previous a week discussions that what the various kinds of ancillary support that can be provided by the virtual synchronous generator. So the various ancillary support mechanism that can be provided are frequency support, yeah, so frequency support, inertia support, reactive power support, or voltage support. Then it can also provide black start support. So these are the various ancillary services that can be provided by this virtual synchronous generator. So here we will be basically seeing the frequency and the inertia support. Now, why do we require this inertia support? So this virtual synchronous generator is nothing but a energy storage concept. It is an energy storage device. So earlier we had synchronous generators, large synchronous generators connected to the thermal power plants and all. So they had huge rotating mechanical parts which had stored energy with them. So in case of any disturbance in the system, so instantaneously the first reaction or the first support used to come from the energy stored in the rotating mass of these machines. And after that, you had the primary frequency control, secondary frequency control, the AGC, tie line power control, those all things. But the first thing that used to come in rescue for any imbalance in the system was from this energy that was stored from the synchronous generator. Now, what happened is with the addition of the renewables and the retirement of the synchronous generator, the inertia that was available with the system is going down. So now what will happen when you don't have enough inertia with you? Whenever there is a little mismatch in power, little mismatch in power means between the generation and the load, then the frequency will basically vary largely. It will shoot up or shoot down because it cannot instantaneously receive that support from the synchronous machines. So for that, we are now using this virtual synchronous generator, which can provide this virtual inertia support to the inverter-based resource connected power system. So that the frequency will not vary much in case of small disturbances in the system, within the system. So to see the performance of this VSG, we basically take the IIT Roorkee distribution system. So you can see the single line diagram here. So this is the grid, the utility. Then we have two diesel generators connected here. There are various feeders you can see here connected that are connected at various locations, and these are the transformers that are connected. And apart from that, we have battery locations, possible battery locations. So you can see ABCDE, five possible locations for battery deployment. Apart from that, you can see large amount of PV penetration throughout the system. So you see there is large PV penetration. Now, these PV are intermittent sources, we know very well. So they can basically challenge the system operation in case of voltages also. So to manage them, we have to deploy a battery in the system. So the components that are used in this setup was first is the BESS, a battery energy storage system that is connected in the grid connected mode. And what it can help in the increased addition of the PV by handling their intermittencies. We can add more PV sources to the system. Then it will in turn help in voltage regulation. So whenever you have excess generation from the PV sources, it may lead to over voltages in the absence of battery. But when you have the battery with you, it can charge and avoid those over voltage fluctuations. Similarly, it's in its absence, it can discharge and also at the same time maintain the voltage. It can also help in peak load shaving, means in the time period of peak load, the battery can discharge to supply the peak load of the system. Then it will then again help in providing uninterrupted power supply. Then next thing you have what is the capacity. So a total of 800 kilowatt capacity is planned to be deployed at five different locations that we saw in the previous slide, right? So A, B, C, D, E are the five locations, and the total capacity for the five locations is to be around 800 kilowatt. Then we have the virtual synchronous generator. So it is in the grid supporting mode and of 2.5 megawatt capacity. Then the various types of load that you have vary as the various departments that are at the IIT Roorkee. Then there are some residential apartments, there are hostels, and the total load of the IIT Roorkee system comes out to be around 7.8 MVA. And then we had two DGs. You see here, we had these two DGs with us. Their total capacity is around 6 MVA. And for this demonstration purpose, we are considering a 4 MVA DG. And then for the PV system, we have around 2.8 megawatt capacity of PV connected at 35 different locations across the campus. And they are operating in the MPPT mode of operation. That means we are not curtailing any power or potential from the PV because we have the battery with us. So coming to the lab setup here, so the in the RTDS we are burning the IIT Roorkee distribution network. Uh, then the semicron converter is used as the VSG. Earlier it was used as the inverter in the previous demonstration. Here it is the virtual synchronous generator. Then this performance of the VSG is controlled using this FPGA based controller. Then this is the PCC or the MCB. You have then the power amplifier and the RTDS racks here. So here two case studies were considered. The first was disconnection of PV panels. So let's say we saw right that there are around the capacity of 2.8 megawatt capacity of PV is there at 35 different locations. So let's say these PV generation, what happened? Yeah. Let's say these PV panels are disconnected from this. That means your generation will drop, which means what will happen? The frequency will also drop. So this frequency drop in frequency is effectively managed by the virtual synchronous generator. The second case study was increase in the induction motor load. In the second one, the load on the system was increased gradually. And again, we saw that the VSG could handle this increase in load by discharging. Then lastly, we saw the demonstration of peak energy management using storage. So you see, if you see the power versus time curve, so this is the PV generation. So that is from you see morning to the evening, and during the night time the PV is zero. This time PV is zero, and then that this is the load curve. So you see that the peak generation is this point, and this is the peak load. The peak generation is not coinciding with the peak demand period. So what we can do, basically we can use the storage, and this peak generation we can, during this duration we can charge the battery, and we can discharge the battery in the peak demand period. Battery in peak demand period, and we can charge the battery during the peak generation or PV. By doing so, basically, we can do the peak energy management of the system. If we had no battery, what would have happened? That during this period of peak generation, you would have to curtail the renewable, and in the peak demand period, you had to curtail the load. So these unfavorable curtailments of both the renewable and the load can be avoided using the storage. So the battery can provide various services to the system, and it can help in voltage control. It can help in managing because we had seen the battery has a four quadrant operation, right? What is meant by four quadrant operation? If we say that this is the P and Q capability curve, basically, if we draw for a battery, so the operating region for the battery is in all the four quadrants. That means it can inject and or absorb both P and Q. But if you remember, for conventional synchronous generator, it is a two quadrant operation because it can only inject P while it can inject or absorb Q. But the battery can do both. It can inject and absorb both P and Q. That's why that is the four quadrant operation that we say for the battery. And hence, basically, we can use this reactive power to control the voltages of the system. Then it can help in managing the stochastic power generation from the PV that we saw in the previous one also. It can have help in the peak load shaving that we discussed in the previous one. Then it can also help in minimizing the power losses, because instead of traveling, this is giving you the option of localized power supply. That means near to the load only you have the generating source. That's why the power did not travel over the long distances in the feeders, and hence the losses can be avoided. Then it can also help in the line loading in the distribution system. And lastly, it can help in the real-time voltage variations within the PV generation. So this voltage support uh, is done in various time scale of operation. So let's say near real time, and this is, let's say, day ahead. So basically in the day ahead, depending upon the forecast of generation and load, depending upon forecast of generation and load, we manage the voltage using various devices such as your OLTC or then your inductors, capacitors, synchronous condensers, various FATS devices. So various sources of Q basically. And then, so this is done using the forecast. But in the real time, the actual generation and the load can be different from the forecasted values. So to manage the differences between the forecasted and the actual values in the near real time, we use various control logics to manage the voltage. Whereas in day ahead, basically we use various optimization techniques to calculate the reactive power support from various devices to for voltage support. And in the real time, we then use various control algorithms. So this was the lab setup. So basically, this is the complete storage that is done here in this box. Then the storage is basically then added to the IIT Roorkee distribution system that is burned in the RTDS here. So you have the IIT Roorkee distribution system in the RTDS, then this physical device of battery energy storage that is added to the IIT Roorkee distribution network. So we have various government approved smart grid pilot projects that are coming up in India across various regions. So you can see around 12 pilot projects are being carried out by the Ministry of Power. So what changes are basically being done here is basically the distribution systems are now being equipped with advanced metering infrastructure, that is your AMI. Just a second. Yes. So basically smart meters and other metering requirements that are being added in the distribution system. Then we have various power quality management functions that are being added, outage management systems, peak load management, and then addition of distributed generation. So these all changes are being added through various pilot projects for the transitioning of the conventional grid to a smart grid. Now, what are the various areas in the research and development of the smart grid are basically in the smart grid operation, control, and protection. So, the operation and control of large, medium, and small scale renewable sources, then protection for AC and DC microgrids. So we saw that due to the addition of the distributed generation, we have bidirectional power flow in the system, and this bidirectional power flow challenges the protection schemes that were earlier being used. So we had to go for adaptive protection. Otherwise, we saw that it lead to various maloperation in the system, and also we need to study the protection schemes for the DC microgrids and smart grids. Then we had wide area monitoring, protection, and control. Then we require various energy management techniques for basically managing the peak load or various demand response activities that can be done. Then the supervisory control of network with multiple micro and nanogrids. So we had seen that in case of multiple microgrids, they can form a network of microgrids and support each other by basically forming clusters. So those all will require sophisticated control algorithms to be built. Then we had network analysis and power flow, optimal power flow. Basically, the addition of various new resources such as the modeling of the PV, modeling of the generation, distributed generations, battery. So then the analysis for this AC and DC hybrid systems, they require new algorithms for load flow and other studies so that are to be developed and are ongoing also now. Then modeling and simulation of large power studies, including the cyber systems. So basically, what we are doing in the smart grid is we are at each and every point we are adding communication to the system, to the physical system, which in turn is leading to addition or creation of large amount of data in the system so that data can be manipulated. We had seen in the lectures can be manipulated by various cyber attackers to hamper the operation of the grid. So we need to develop robust control algorithms which can differentiate between the actual fault and the malicious faults that are deliberately being injected into the system by the cyber attackers. Then a seamless grid operation involving TSO and DSO. So basically, the management of this numerous distributed generations that are being added in the system, they are usually done in the distribution system side. Now, managing these resources will require the addition or the emergence of a new entity called the distribution system operator, which will look after the operation of the distribution system and also see that how these resources can be added effectively without hampering the grid network constraints. Additionally, they can also help in providing services to the transmission system. And these all are to be done through the distribution system operator. Then forecasting of renewables and loads. So to manage the intermittencies of the renewable generation, we need to have sophisticated forecasting tools with us so that we can accurately predict what will be their output in the day ahead and so that we can be prepared for the scenarios. Now, what are the distributed energy resources, storage, and deployment issues that are within the smart grid? So, the first thing is various policy, regulatory, and market design issue. So, as we know, as these are these are new scenarios that we are facing now with the addition of distributed energy resources. So we do not have concrete rules and regulations for their addition, like where should be the added, what should be the voltage level where they are added, what reactor power or at what power factor they need to operate, and let's say so these are various standards that are yet to be developed and yet to be mandated by the grid, and then the emergence of other entities such as this distribution system operator or microgrid system operator. So, what will be their role? What should be their aims and objective? So, that has to be fundamentally laid down by the government. So, those policy and regulatory kind of rules are yet to be designed for the integration of these renewables to the system. Then demand side management with optimization and forecasting techniques. So this is also a open challenge. So Basically, now we are each day we are working on how we can develop better forecasting methods to predict the wind or the solar at various locations. Then with the optimization techniques for the demand side management, so we now have to consider the AC power flows because we need to also take care of the voltage. So earlier we used to use DC power flows because we were mostly focusing on transmission system studies where the voltage issues were not so prominent with us because the effect of reactive power and the active power can be decoupled very easily in the transmission system. But coming to the distribution system, the active and reactive power cannot be decoupled in the same way, and hence these require considering them simultaneously and developing the algorithms in the way that both the active and reactive power are being considered. Then inertia issues for the renewable that we discussed, like due to the retirement of the large thermal power plants, synchronous generators, we may have issue of inertia. That means the inertia of the system is reducing. So we need virtual synchronous generators to mimic their performance in their absence. Then optimal mix, setting, and sizing of energy storage at various level. So what do you mean by optimal mix, sizing, and setting and sizing is basically this is a planning study that we do year ahead, mostly 5 years ahead or 10 years ahead. So depending upon like what will be the mix of generation with you, what will be the load that will be there. So we need to decide that what kind of energy storage. So we know that they can be of high power type or high energy density type. So like uh, what is the capacity that you want, what capacity of energy storage you want want to add to the system. Once you know the capacity, then you have to decide at which location of the system or the grid you want to deploy this storage. Now you also need to decide the type of the storage, whether it you want for high power application, high energy application, or both. In case of both, you have to decide like what percentage of capacity are you keeping for high capacity applications and what percentage for high energy density application. So those kind of decisions are to be taken. Then electric vehicle interfacing issues for vehicle to grid, grid to vehicle, and vehicle to home. So again, these standards for charging and discharging of batteries, basically with the electric vehicle, are to be again mandated by the grid. So so that basically you can universally, if once you have a concrete kind of standard, then it is easier to charge or discharge the batteries. Like earlier, you see we had USB type of cables, then Type C type of cables. So due to the differences in this type of cables, the charging was not a smooth process. But now you can see as we moved ahead, the universal standard of Type C has been adopted. So now you do not require different chargers for charging different types of equipments. A universal Type C charger can be used to charge your even watch, your earphones, your mobile phones, your tablets. So you do not require five kind of chargers for five different devices. So similarly, if you have one common standard, so let be the EVP of different makes. So you have different companies with you. You have Ola, you have Bajaj, you have different companies that are manufacturing EVs. But since they will have one common standard, so you do not require different chargers for different batteries that are being manufactured. And similarly, once you have the universal standard, then the vehicle to vehicle charging or discharging can be done in the smooth and efficient manner. And next is using the energy storage for meeting the transient requirement. So for that, basically you need to install a storage with high power type, high power density type, such as your Supercapacitors. So these will help in transient performance means for frequency because they can charge or discharge quickly. They can charge and discharge very quickly. Now coming to the Q&A session. So the first question is the high deviation in power in case of asymmetrical fault is mainly due to what? High variation in DC link voltage, high negative sequence current, high variation in speed, or high deviation in flux. So we had seen that due to the asymmetrical fault, you will have the presence of negative sequence components. So the correct answer is high negative sequence current. The next question is the typical time step for EMT simulations is 10 to 20 microsecond, 50 microsecond. It is less than 50 microsecond or in between 1 to 50 microsecond. So for EMT type simulations, we are basically doing for transient type of studies, and they can be the time step can be very small in the order of 1 to 50 microsecond. Now for a transient study, the power electronic converter needs to be modeled in small time step, average modeling, any of the above, or none of the above. So we require accurate modeling of a power electronic converter for transient time studies. So hence we use the small time step type of modeling. Which type of energy storage is suitable for peak energy management? High power density, high energy density, or both or none? This we have discussed, right? For peak energy management, you require to store the energy for longer periods at greater efficiency. So for that, you require applications as energy storage with high energy density type. In a passive distribution system, voltage problems are mostly evident in the head of the feeder, end of the feeder, across the whole feeder, or none. So in passive distribution system, basically we had radial type of distribution system. So gradually the voltage will drop towards the end of the system. So let's say if the head is at 1.0 per unit, so you'll have some drop here, let's say 0.99, 0.98, and similarly. So the voltage at the bus that is located farthest from the head means which is connected to the upper stream that is connected to the transmission system. So this is known as the head of the distribution system. So which is located from farthest of the head will have the largest drop. So hence the voltage problems will be evident in this region. So towards the end of the feeder. Um, yeah. In the peak energy management demonstration, the grid emulator is acting as a DC source, AC source, electronic load, or energy storage. It was acting as the AC source plus the energy storage. Now coming to some other questions. Uh, First is what is or are the important elements of a PHIL setup? The options are power amplifier, GTAO card, voltage current sensors, or all. So what will be the answer here? So we have seen in all the demonstration, these components were common, right? So this power amplifier, GTAO and GTAI card, and then voltage and current sensors to basically monitor the device under test. So all of these are important elements for the power hardware in loop setup. The next question is match the following type. So first you have doubly fed induction generator. You have real-time digital simulator RTS. You have PHIL. You have FPGA. Oh, basically you have to match with the full form for the acronyms. And you have HIL. And here you have field programmable gate arrays, hardware in loop. Then you have real-time device simulator. Then you have power hardware in loop, doubly fed induction generator. Then you have real-time digital simulator. So if we match this, so DFIG is doubly fed induction generator. RTDS is real-time digital simulator, so F. Then that is power hardware in loop. Then FPGA is field programmable gate arrays, and HIL is hardware in loop. Then next is identify the correct statement. First is maximum solar injection during off peak load hours may lead to under voltage. Next is peak load hours with little or no solar power may result in under voltage condition. Reverse power flow is not possible in active distribution, is not possible in active distribution system, or all are incorrect. So let us see one by one. So maximum first one is maximum solar power injection during off-peak hour may result in under voltage. So no, if your PG is more and load is also low, that means it will lead to over voltage. Then peak load hours means PD is more, and with little or no solar power, PG is less. So that will lead to under voltage. So this is correct. Reverse power flow is not possible in active distribution system. So reverse power flow is possible. We have seen time and again. In case of excess generation, you can have power injecting back to the transmission system. So yes, reverse power flow is possible. So the correct answer is B. The next is that battery energy storage has been proven to be an effective solution for voltage control, flattening of load curve, reduction in power losses, or all. So we have seen that battery time, we discussed that it has both active and reactive power support capability. So it can help in voltage control, it can help in flattening the load curve by basically absorbing or charging in case of peak demand and discharging during peak load hours. It can help in reduction in power losses by providing the power locally. So all of these are correct. All of the these statements are correct for battery. The next question is okay. Let me. What are the smart grid R&D areas under ICT, Information Communication Technology, and Cybersecurity. First is seamless grid operation, involving transmission system operators and distribution system operators. Reliable wired and wireless communication technologies. Then coordination and control of multiple converters. B is all of the above. So it is asking only for information communication technology and cybersecurity point of view. So seamless grid operations with TSO and DSO, that was for policy and regulation frameworks point of view. Then reliable wired and wireless communication technology, that is true, that is coming under ICT. Coordination and control of multiple converters, that is not true. So B is the correct answer. Next is, what are the primary goals of Indian smart grid pilot projects in distribution system? Incorporating advanced metering infrastructure, incorporating outage management system, lastly all of the above. So this we had seen, all are correct, right? AMIs, outage management system, peak load management, distributed generation, and what else was there? Storage, I think. So all these are correct. The next question is, what is or are the probable causes of errors during PHIL? First is accuracy of measuring sensors and their related scaling factors. Scaling factors associated with GTAO and GTAI of RTDS. See both D none. So obviously we monitor the device under test using the sensors, the voltage and current. Basically, we were sensing and giving it back to the RTDS through the GTAI card. So that will affect the operation in the PHIL. Scaling factors also will basically when we were going from uh, RTDS to GT AI card and similarly back to the RTDS through GTAO card. So we had a scaling factor at each both locations. So that accuracy will also affect the PHIL setup experimentation. So both is the correct answer. The next is the excess load demand in active demand in active distribution network result in voltage sag and reverse power flow, voltage rise and reverse power flow, voltage sag only, or voltage rise only. So when your PD is greater than P gen, so that will lead to drop in the voltage, right? So voltage sag. And since you have deficit in power generation, obviously you cannot inject power to the transmission system, so there will be no reverse power flow. So it will be voltage sag only. What is or are the main objectives of IIT Kanpur Smart City? Demonstration of future capabilities of smart grid, renewable energy integration in the form of grid connected PV, advanced metering infrastructure, or all of the above. So it is for demonstration of feature capabilities of smart city, for integrating large amount of PV, for advanced metering infrastructure. So the correct answer is all. The last question is the power flow control of DC microgrid falls in dash layer of control. So primary, secondary, tertiary, or zero level. The correct answer is tertiary. Before closing today's session, we will just see one transformation between this ABC, alpha, beta, and DQ frame of reference. So we know that the ABC phasors are separated by 120 degree, and converting this ABC quantities to the alpha beta frame. So this is the alpha beta phasor at 90 degree. So converting this I alpha, I beta to the I ABC frame. So you see this I alpha is exactly coinciding with IA. So this will be 1 and both other components will be 0. Sorry, this will be, yeah. Now the next, when you decompose this I alpha or IB to alpha beta frame. So when you decompose this IB, basically B, it will be like this. So this alpha is opposing this alpha. So it will be minus sign here, minus half. And this beta is in phase with the beta axis. So it will be positive. So that is giving you root 3 by 2. And then the angle basically sine 30 cos 30. So 1 half and root 3 by 2 are coming from that. Then when you decompose this C to alpha and beta, so it will be this. So again, alpha is opposite to this alpha and beta is opposite to this beta. So it will be both negative. So minus half and minus root 3 by 2. And to scale their magnitudes, you have to have a minus 2 by 3 factor here. So this will convert this alpha beta frame to the IABC frame. Now similarly, you can convert again this alpha beta frame of reference to DQ frame. So DQ frame is a tan angle theta with this alpha. So this will be the DQ axis. So this ID and IQ you can again calculate with the help of I alpha and beta using this scaling factor. So this is the relation between the ABC frame, alpha beta frame, and the DQ frame. So this brings us to the end of our discussion for the week 12 and also for the course of Smart Grid Basics to Advanced Technology. So if you have any doubt in any of the week content, we can discuss now. We have time. If you have any query, if not, then we will close for this session basically for this semester. So I wish you all the best for your exams and hope this content was useful to you all. So thank you for joining. Thank you, sir. Wish you the best.